नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT जेईई एंड नीट। सबसे पहले मैं आप सभी का शुक्रिया अदा करता हूं। आप लोगों की वजह से आज लगभग 25 दिनों में हमने 5.5 के व्यूज़ पूरे किए हैं और 260 सब्सक्राइबर भी हमसे जुड़े हैं। आज मैं रियल गैस में इंटरमॉलिक्यूलर फोर्सेस ऑफ इंटरेक्शन के बारे में डिस्कस करूंगा और कोशिश करूंगा कि आप रियल गैस को ज़्यादा आसानी से समझ पाएं। साथ ही मेरा यह प्लान है कि मैं इस चैप्टर को पूरी तरह से आप लोगों के साथ डिस्कस करूं। कोशिश रहेगी कि आपको इससे लाभ हो। इंटरमॉलिक्यूलर फोर्स ऑफ इंटरेक्शन मीन्स force of interaction between atoms or molecules. Like when we are saying that there is inter football match, it is a match between two teams. Same way when we are saying intermolecular interaction, it means that it is interaction between two molecules. If we are saying that there is interaction between ion and molecule, then this is not intermolecular because one is ion and other is molecule. Ion dipole or ion induced dipole is not intermolecular interaction. For intermolecular interaction there must be two molecules, so interaction between molecules is known as intermolecular interaction. The second point, interactive forces acting at a particular instant are of both type, attractive as well as repulsive, but the net resultant may be either attractive or repulsive or zero. So let us understand this point with the help of an example. If I am taking a real gas, if the volume of the real gas is very large, when the molecules are far apart, there is no interactive forces between the molecules. So under that condition we will say that the real gas will behave like an ideal gas, because in ideal gas there is no interactive forces. Now if we compress the gas, and when the molecules will come nearer to each other, there is force of attraction between the gas molecules. And if we compress the gas further, a time will come when the pressure is very high, and under that pressure, high pressure condition, repulsive forces are dominating. So for the same gas, when the volume is very large, it is behaving like an ideal gas, means there is no interactive forces. Then when we are compressing it, when the molecules are coming nearby, then the attractive forces are dominating, and under high pressure condition repulsive forces are dominating. So these intermolecular interactions between the molecules is because of electrostatic force of attraction between the nucleus of one molecule with the electron cloud of another molecule, or vice versa. And the repulsive forces is because of electrostatic repulsion between the nuclei of two molecules and the electron cloud of two molecules. Variation of potential energy between two molecules with separation distance. On y-axis there is potential energy, on x-axis there is separation distance. A real gas is present in a container of large volume, and the distance between the real gas molecule is large, so there is no interactive forces between the real gas molecules. But now we are compressing the real gas. As we compress the real gas, the molecules will come nearer to each other. So due to decrease in the distance between the nucleus of the molecules, the repulsion, electrostatic repulsion between the nucleus will increase, or the electrostatic repulsion between the electron cloud of the molecules will increase, and because of that this repulsion is going to increase on decreasing the distance. So the upper graph is related to force of repulsion, and because of force of repulsion the potential energy of the system is going to increase. When we are compressing the real gas, the molecules are coming nearer to each other, so the distance between the molecules is decreasing, and because of that the electrostatic force of attraction between the nucleus of one molecule and the electron cloud of other molecule is going to increase. Due to increase in force of attraction, the negative value of potential energy is going to increase. So the lower graph is related to force of attraction. As we are decreasing the distance between the molecules, the force of attraction is also increasing. The middle part of the graph, which is red in color, is the net resultant of force of attraction and force of repulsion. So when the molecules are far apart, there is no net interactive forces, or potential energy will be zero, but as we are decreasing the distance, till here the potential energy is decreasing, means the force of attraction between the molecules is increasing, and after that the potential energy starts increasing. So repulsive forces are dominating. Before the bottom point here, when we are moving from a large distance to the bottom point, the potential energy is going to decrease, and then the potential energy is going to increase. So the middle graph is telling about the net potential energy variation with distance for a real gas. Till now we have discussed that if the gas molecule is hydrogen gas, which is a non-polar gas, when the molecules are far apart, there is even distribution of charge on these molecules, and these molecules seems to be symmetrical. When we are compressing the gas, these molecules will come nearer to each other, and the distance between these molecules are going to decrease. As the distance between the molecules are decreasing, the electrostatic force of attraction between the nucleus of one molecule and the electron cloud of other molecule is increasing, and this portion is dominating. Because of that, the attraction between the real gas molecules are increasing. And if we compress the gas again and again, a time will come when the pressure of the gas will be very high, when the molecules are touching each other. So when the molecules are touching each other, at that point of time, the electrostatic repulsion between the nuclei of two molecules and the electron cloud of two molecules will be dominating. So the net repulsive force will act between these molecules. In case of an ideal gas, when we are calculating the pressure of an ideal gas, the pressure of ideal gas depends on three factors. We are using ideal gas equation to write PV is equal to nRT. From there we can say that pressure is equal to nRT by V. So the pressure of an ideal gas depends on number of moles of the gas, temperature of the gas, and volume of the gas. But for a real gas, if we take an example of Vanderwaal real gas, we know the equation P plus Na square A upon V square into V minus Nb is equal to nRT. So in this equation we know that Na square A upon V square is pressure correction, and V minus Nb, where Nb is known as volume correction. So in case of Vanderwaal real gas, if we see that pressure of Vanderwaal real gas depends on what? So we can write that pressure is equal to nRT upon V minus Nb minus Na square A upon V square. In case of ideal gas, there is no interactive forces, but in case of real gas, there is interactive forces, right? So we can say that the pressure of this real gas is going to depend on number of moles of the real gas, temperature of the real gas, volume of the container in which it is present. Apart from that, they will also depends on the factors which will decide the interactive forces like A and B. A is related to force of attraction and B is related to force of repulsion. So the pressure of a real gas will depend on number of moles, temperature, volume, as well as interactive forces between the real gas particle. From the variation of potential energy between the molecules versus separation distance, we can conclude certain things about the interactive forces between the real gas molecules. So we know that the force of interaction is equal to the rate of change of potential between the real gas molecule with distance. Force is equal to minus times of dV upon dr. So if we are discussing here the actual potential energy versus separation distance is shown by the red graph, the middle graph. So in this middle graph, when we are at a large distance, there is no interactive forces, and as the molecules are coming nearer to each other, the force of attraction between the molecules is increasing. So till here at the bottom point, at this point, the force of attraction is increasing on decreasing the distance between the molecules. So till here the force of attraction is increasing. From this graph, using this equation, I can say that if I take any point on this, if I draw any tangent at point on this curve, the slope of tangent will be positive. It means that the force acting between the molecules will be negative. Negative force means there is force of attraction between the real gas molecules. At the bottom point here, if we draw the tangent on this curve, the slope will be 0. Slope is equal to 0. So from here we can say that the interactive forces will be 0. There is no interactive forces between the real gas molecules. And if we further decrease the distance between the molecules, then the repulsive force will dominate. So in this portion of the curve, if we take a point on this curve and draw a tangent, suppose this is the point I am drawing the tangent. So the slope of tangent on this curve is negative. So when slope is negative, we can say that minus dV upon dr is negative, means the force is positive. Positive force means there is force of repulsion between the real gas molecules. So the interactive forces initially will be 0, and then it will be attractive, and then again it will be 0, and then it will become positive. So this is the variation of interactive forces with separation distance between the real gas molecules. Now again, from this curve we can conclude about 2 points. Here from origin to this point, we can say that point A, there is a distance. This distance is known as sigma. So sigma is the distance where the potential energy between the real gas molecules is equal to 0. And in this graph, epsilon is known as the well depth. It's a well, and the depth of the well is denoted by this height, which is, so well depth is telling about the force of attraction between the molecule. If the well depth is more, it means that there is a strong force of attraction between the real gas molecule. If it is shallow or its depth is less, we'll say that the force of attraction will be less between the molecules when they are coming nearer to each other. So this graph is explained by this equation. It is known as Lennard-Jones potential. There are two types of interactive forces. One is related to force of repulsion and the other is related to force of attraction. The variation of force of repulsion is directly proportional to 1 upon r to the power 12, while the variation of force of attraction between the molecules is directly proportional to 1 upon r to the power 6. Sigma is the distance at which the intermolecular potential between the two molecules is 0. Epsilon is well depth and a measure of how strongly the two particles are attract to each other. So let us understand this point with the help of this example. So this is potential energy versus separation distance graph for two inert gases, helium and argon. So we are discussing in a container there is helium gas, and when the volume is large and we are compressing the gas, so the molecules are coming nearer to each other. This is the graph related to this. For this graph we can see that the well depth is very small. So we can say that the force of attraction between helium molecules will be less. While in case of argon, when we are moving from a large distance and we are compressing the gas, we are putting the gas particles near to each other, this well depth is very large. From there we can say that the force of attraction between argon and argon molecule is more than the force of attraction between helium and helium molecule. Repulsion forces are significant only when the molecules are almost in contact. Attractive forces are effective when the molecules are apart over several molecular diameter. If you read NCERT, they have mentioned that the force of attraction and force of repulsion are short range forces, and force of attraction will be valid when the distance between the molecules is of the order of 500 picometer. Attractive intermolecular forces, because we are discussing two type of intermolecular forces. So attractive intermolecular forces are also known as Vanderwaal forces. Vanderwaal forces are of three types. We will discuss the three types of Vanderwaal forces in our next episode of real gas. So here again I want to mention that between the real gas there are two type of interactive forces, attractive and repulsive. Attractive intermolecular forces is known as Vanderwaal forces, right? There is also repulsive intermolecular forces, and those forces act when the molecules are nearby each other, when they are at a distance of equal to their diameter, or when they are touching each other, then those forces are dominating. If this information is useful, please like and subscribe our channel. Thank you.